Hello and welcome to today's DeepSense Discovery session. I am joined by Fergal Odenica from IBM, and we're going to talk about unlocking the potential of machine learning. And he'll tell you about his experience at IBM and all of the great research that he does. And he's here because IBM is one of our partners. So DeepSense has great funding from supporters like ACOA from the federal government of Canada, the province of Nova Scotia, Ocean Frontier Institute, COVE, the Center for Ocean Ventures based out of Nova Scotia, and Dalhousie University. And the reason why we exist is we have IBM infrastructure that we own and operate to explore high performance, or we use for high performance computing for machine learning and artificial intelligence. And the reason why DeepSense exists is because we partner with academic researchers and ocean companies, and we enable them to explore, trial, adopt, and develop artificial intelligence, machine learning, and interesting visualizations that they might not be able to do otherwise. The reason why we exist is because a lot of companies can't always find a use case. They don't have the skills and capacity, or maybe even their infrastructure and access to software is pretty limited to try to build out complex machine learning problems. So at DeepSense, we have students, we have resources, and we have that fancy IBM infrastructure that we use to help companies solve problems. And so today, if you want to rewatch this session or share it, because I know that you're going to learn a lot and you'll be obsessed with sharing this, please check out our DeepSense YouTube page. This is your tiny URL, or you can find it through our website and Twitter and all sorts of other things. So thank you very much for joining us.
Great. So what I want to talk about today is some of the work that we are doing at IBM Research around physics-informed machine learning. And a lot of this is part of an exploratory science challenge that we are working on at IBM. And in effect, what exploratory science challenges in IBM is the mechanisms that we use to develop the technologies of the future, the solutions and assets and offerings that we expect IBM business units to be offering and selling in 1, 2, 3, 4 years time. So it gives you an idea of where we see the physics-informed machine learning space currently. So I'll go through in a bit more detail in the talk, but machine learning and its value, its applications, its use, in the last decade, it has made enormous strides. I mean, it's part of every facet of our life, I think, at this stage. And where the physics-informed component we see huge value is to bring that same value and that same disruption to industries that have not yet received the full impact of machine learning, primarily due to the challenges of data, getting data, the expensive data, etc. And some of those are primarily some of the scientific applications and also the engineering applications. And we see huge potential there. So what I'm going to do today is I'm going to give a very quick overview of IBM Research, what we do just at a high level, and then go into the details of the details of the talk and how we are leveraging physics-informed machine learning for some of our pilot studies and applications. So if I can go ahead. So this is an overview of IBM Research. So in total, we have about 3,000 researchers, which is about 1% of IBM. So it's relatively large, but very small compared to what IBM is. We have 19 locations across 6 continents, with our headquarters in Yorktown in upstate New York. And in effect, what we do in research is we have 2 complementary focus, I believe. One is where we are servicing and developing the current strategy of IBM and developing solutions that develop and further IBM strategy and solutions related to cloud, artificial intelligence, and these related offerings that IBM are currently offering to market. And 2, developing the solutions of tomorrow. So examples of those would be quantum computing, for example. We have a strong focus on the future of climate at the moment and how we as an enterprise-focused company can provide solutions that help society, companies, etc., adapt to a future climate, etc. And within that, then at individual locations, there are distinct geographical focuses. Etc. So, for example, some of our African labs have a very strong focus on blockchain solutions and how these type of components can be leveraged and applied for industry solutions, so to speak. So here, I just want to give a very brief overview of some examples of what we're doing in research from an environmental perspective, or one aspect here is the weather company, which is an acquisition that IBM made about 5 or 6 years ago. And IBM, the weather company, now generates 25 billion forecasts per day. Its most recent model version is IBM Graph, which provides a global weather forecasts it's a weather model at, I believe, 3 kilometers resolution globally, which in terms of computational complexity, in terms of the scale, precision, resolution of data is at a global level, it's quite impressive. And that often ends up being a fundamental underpinning of a lot of our environmental solutions. So, for example, I work quite heavily on aquaculture at the moment, actually working with Dalhousie quite closely on this, and weather and how we can use weather to inform on aquaculture operations is a fundamental part of that, and it provides a extremely useful tool to allow for better decision, better information on current conditions and upcoming conditions by that combination of extremely high resolution, high accuracy weather forecasts at the extremely localized level. And the other thing that I want to talk about a little is what has become a big focus in IBM Research in the past 12 months particularly, and what is termed the urgency of science. And I don't think there's ever been a time where science has had more urgency, so to speak, has had more, there's been a stronger need for scientific solutions and scientific impact and scientifically driven decisions. So I think we've had a very good example of that in the past number of months, as we have seen the distribution of vaccines, et cetera, in response to a global pandemic. Equally, there are more pressing challenges ahead for us, particularly in terms of climate and what that means for industry, society, et cetera. So what is fundamental there is how we respond to that and how we leverage science and move science from the academic, the theory side of science to that real application and to that real impact. And I believe that is something that we can address today with this combination of physics plus machine learning, where we have these very established scientific knowledge, scientific understanding, scientific descriptions of many systems. And by combining that with the more emerging or the more recent advances done in data science, machine learning, etc., the potential to allow for very concrete solutions that addresses really fundamental challenges, because developing machine learning solutions that do better targeting advertising or do better Netflix recommendations, etc., it's quite nice, but it will not have the impact that is necessary for addressing some of the challenges that we are currently facing around environment, around climate, and around related activities and adapting to those. So to move ahead and go a bit deeper into physics-informed machine learning and to position it a little better. So this slide, I think, is familiar to many of you. What machine learning is, what it's applied to, etc. And we can consider it in terms of two key components. So component one is around the data. Okay, we need the data to train our models, to learn relationships, etc. Andrew Ng has quite a nice, he gave quite a nice talk recently that I was watching around ML ops. He refers to it in similar to DevOps as a development procedure. And what he highlights there is the importance of data for machine learning, and oftentimes for applied machine learning, value and improvement in model performance is often obtained by adapting, massaging, generating, and augmenting data rather than working on the other side of the machine learning aspect related to the algorithm. So the feature extraction, the addition of new data, how we combine, manipulate, transform data to be amenable towards a machine learning algorithm, and then the predictive component, the deployment of that model as new data comes on stream, etc., generating prediction. And we can do this in the supervised or in the unsupervised learning approaches, which from an unsupervised perspective, clustering or recommender systems would be a very obvious example there. So let me move forward. And so this, in effect, summarizes what we are doing here. We have our observations, we have our target, and we generate our machine learning model. So we generate or learn F that gives us the relationship between our observations and our target variable. So this is all pretty standard. So where then we run into difficulties is when we go beyond the issue of learning if a particular image relates to a cat or a dog. If we go beyond the image of if you bought book X, what book might you be interested in next? But instead, if we want to do high resolution environmental forecasting, how do we deploy machine learning systems for that? If we want to understand extremely complex systems, if we want to better understand the processing considerations of various industries such as aquaculture and their associated dependencies on the environment, if we want to make better decisions for industries such as shipping, if we want to do safety assessments of infrastructure, bridges, etc., then how do we obtain data for that? How do we condition and develop and augment the data towards that? And how do we deploy a machine learning model that is both robust and trustworthy in those critical, highly complex situations or scenarios? And this is an overview of these situations. So the first part is what unifies these problems and these applications, and what unifies them is quite straightforward. Right? These are all extremely complex, multi-physics, multi-scale, etc. We can't currently simply deploy a model that gives us a high resolution, highly accurate representation of the environmental systems such as oceans, etc. We can do at specific scales, etc. But doing it in a generalizable manner is currently not something that we can do from a direct partial differential equation resolved model, etc. And the second part is these are important. So we cannot afford to be wrong in some of these aspects. We cannot afford to be incorrect when it relates to safety assessments of infrastructure, decision support for many industries such as shipping, etc. These require accurate and efficient tools, so accurate and also available rapidly or in real time. And that is where we run into many challenges, and we fall back to much more complex decision making that involves a lot of combination of models, analytics, and backed very heavily by human expertise and intuition and knowledge, etc. So that is where we explore where machine learning can automate these systems, and that is where we run into the challenge that we were discussing earlier around the complexity of getting data for these systems. So a number of years ago, there was a popular article in, I think it was Wired, in the late 2000s, titled "The End of Science," and the hypothesis there was, in the era of big data, as we have so much knowledge about systems, as data becomes ubiquitous, then we no longer need scientific theory. We can just develop data-intensive representation of these systems, and we can progress from there and characterize the systems in that manner. That has not happened to any real extent for these type of systems, due to the challenges of data and due to the complexity of data as well, in terms of data comes in many different forms, different resolutions. So if we take the ocean as an example, we have combinations of point-based sensors that are measuring things like temperature, salinity, etc. We have gliders that are sampling at different temporal resolutions, at complex trajectories across the ocean. We have satellite data that is representing at a much coarser resolution spatially, but at much larger spatial scales. We have the issues that satellite data may have in terms of missing data and cloud cover impeding measurements, etc. So it becomes a question of how do we operate in these scenarios where the direct modeling approach is infeasible, and in effect we have the challenges of small data in a big data world, and how can we combine those mechanisms to respond to these complex systems and situations. So how can we balance what we know and what we can do from a direct modeling perspective with what we know and we can do from a data-driven perspective, also in some form of optimal combination of both. So this is an overview of what are some of the fundamental challenges facing machine learning in these systems. So one is the complex representation of the systems, and the mismatch between variables or the mismatch between variables or independent features and the observations or labels or representation of the true state, that in effect precludes a direct or poses a huge stumbling block to a direct application of machine learning approaches. And the further challenge then related to the challenges and the potential for overfitting, and the challenges related to generalizing. So in many of these systems, we are not that interested in the mean or what is happening on day to day. We are focused and interested in what is happening during extreme events, what is happening if we have an environmental event, what is happening during high waves, flooding, etc. So how do we represent those within a data-driven approach that is, in its simplest form, conditioned on the mean rather than conditioned on the actual events that we might be possibly most interested in. And the final challenge here is around interpretability and trust, which follows directly from the first two challenges. So emanating from that, can we combine what we know about a system and what physics tells us about a scenario, can we combine those to communicate trust and communicate solid scientific foundations to move beyond and to enhance the robustness and trustworthiness of our models. So again, it's going back to much of our direct modeling approaches are underpinned by very robust theoretical approaches, etc. Data-driven approaches have a much more heuristic application where aspects like extremely deep neural networks, they work very, very well. We don't have a very strong theoretical grounding or theoretical representation of error boundings on those, or a very strong theoretical representation of why they represent a useful or a robust representation of a given system. So it's a question of, can we combine these two aspects? Can we combine these, what we know from a theory or physics approach, with the advantages of machine learning to, again, address this problem related to trustworthiness, robustness, performance in performance during extreme events, performance on small data sets, etc. And again, bridge the gap between where we currently apply machine learning to the many, many industries such as science, engineering, etc., where we currently don't have this, the same level of impact and disruption. So this is a representation, this is a slide that I took from a talk given at Sandia, I think it was towards the end of last year. So what it looks at is a representation of a scientific machine learning versus where it falls between the data-driven approach and the traditional physics-based approach. So if we consider the traditional scientific computing, we have a small amount of data that we use to, in effect, calibrate and validate our models. So we deploy a numerical model of a particular bay or estuary, for example. We set up boundary conditions. We set up boundary conditions, initial conditions, etc. We run it against a test period, and we calibrate that model against a sparse set of observations. A traditional machine learning, on the other hand, is we have a large volumes of data. We curate, massage that data. We select a particular machine learning algorithm. We train that and we deploy. And then the scientific machine learning representation, where we have some knowledge on the system, we have some unknown relationships or closures, and we have a small amount of high fidelity data. So we wish to impart what we know from the model representation, what we know from theory, what we know from physics, together with the small volume of data to represent the system. So in effect, one can think of it as a training with small data representation, and by augmenting what we don't have from a data perspective with what we do have from a knowledge or theory perspective. And so this is, in effect, summarizing what I've been discussing a bit here. It's taking what we have on the right here, on the bottom here, in terms of data-driven models, machine learning, and AI, and bringing it to impact for multiple different industries. And the building blocks are in place, so to speak. We have a couple of 100 years of physics behind us that to characterize the system, etc. We have the IoT aspects and the sensor technologies that is generating data at different scales, and we have the advances that have been done in the past decade in terms of GPUs in terms of the computational infrastructure to enable the data-driven aspects. And there's a few different combination of these. So combinations of the physics-based approaches with the data-rich applications, and the combination of those with the machine learning algorithms and the advances made there in terms of the physics-informed data-driven modeling, where can we learn directly, or can we inform the machine learning algorithm with some information from a physics-informed perspective? So can we guide that, the loss function, can we guide the training of the machine learning approach with specific information from physics, etc. Another area that we have done quite a lot of work in relates to physics-driven surrogate models. So can we use high fidelity simulations to augment the data that we have and to generate synthetic data to allow us to apply data-driven model, to allow us to apply machine learning directly on that data. And what that provides us is, in effect, a reduced order model or a surrogate model of these complex systems that can be run at much reduced cost and much reduced complexity in terms of parameterization and calibration, etc. And this then summarizes some of the things that we wish to achieve with this in terms of the increased learning rate with the input of physical laws. So can we learn faster? And what that in effect provides us is, can we learn on smaller data by constraining the learning functions? We want to maintain the fidelity of the data as much as possible by, can we restrict that the model must respect certain specific conservation laws. So for example, here, if we are deploying machine learning to characterize environmental systems, such as fluxes or wind speeds or something of this nature, can we ensure that there is continuity of mass across spatial scales and across temporal scales that are respected, that are consistent with what we know from a physical perspective? And the final part then relates to reducing the computational effort of large-scale models. So that in effect relates to, can we develop accelerators of specific components of modeling systems? So a common challenge there from an environment is turbulence closure is a challenging and complex aspect of many environmental models. Can we replace that, or replace some parts of that, with machine learning based accelerators that allows us to deploy the complex model at reduced computational cost? And these are the three different approaches that I want to discuss a bit today related to the physics-informed machine learning side. The first relates to the constrained optimization. So can we use physics knowledge to better guide what the model is learning and how it is, how the loss function is optimized? The second part relates to the reduced order models. So again, relates to the lightweight machine learning versions and how we can integrate those. So how we can use those reduced order models to provide better value to industry and better impact than the high fidelity simulation model provides on its own, or what the machine learning model can provide on its own. And I think an interesting aspect related to this is in the past number of months, there's been quite a lot of attention given in Europe to the concept of a digital twin of our planet. And what that relates to is, by 2030, the European Commission aims to have a complete digital twin of our planet at high resolution at high precision and at high temporal frequency. And they have outlined at a high level what that entails from a complexity perspective, or the tools that are necessary for that, in terms of it naturally requires greater a much richer collection of data and sensor deployments, etc. It requires physics models at a much higher resolution, etc. But what is fundamental also is in the past, to deploy models and simulations at higher resolution, we in effect threw compute power at them, and enabling advances in that manner. That cannot continue in that manner, in terms of due to the energy footprint, due to Moore's law and the challenges that provides in terms of the continuous increase in computational performance that we have got used to, and not potentially not living up to it in the future, etc. So what is required instead is a much more efficient method to resolve these aspects. And that is where a combination of high fidelity models with lightweight reduced order models that resolves at certain times, that resolve certain features, that resolve certain processes, that combination is essential to enabling that digital twin of our planet to be developed and represented. So what we'll start with is the physics-informed constrained optimization approach. So this, in effect, is what we are aiming to do here. So this is a classical machine learning loss function, where we condition our model on the observation with some constraint related to avoid overfitting, or to avoid overfitting. What we do here also is we introduce some physical inconsistency that should not be incurred or should not be exceeded. And instead of our typical loss function, what we aim to do with this loss function is to constrain further with what we know it represents a physical inconsistency. And one prominent example of this, I think this was in 2017. This was a paper related to physics-guided machine learning for lake temperature modeling. And on this image here represents a classical temperature density profile of a lake, where we have warmer and hence lighter water in the surface layers, and with a thermocline or a steep gradient in temperature or density happening at some depth during the column. And underneath that, then there's a relatively stable cooler body of water, which again has a relatively constant density. The physical constraint then that is represented by this is given here, where the density of the surface layer, the density of a layer above, should not exceed the density of a layer beneath. So we can train a machine learning model on this by converting this information into a loss function and combining it with the traditional loss function, where we learn to predict temperature based on labels of temperature or observations of temperature. So in this case, our physics-based loss is simply a sum of our physical violation here. So simply the sum of the difference, the vertical difference of density or temperature must be greater than 0. And this then is introduced as a loss function into the training of the model. So we have our traditional loss regularized on the size of the variation of the weights, together with our physics-based loss, which is directly related to temperature should not contravene this rule related to warmer water or lower density water overlaying colder or higher density water. So that is another example that we're working on together with some colleagues in the Yorktown lab is the idea of super resolution. So super resolution is quite common for image processing, etc., with the idea of can we use machine learning to improve or increase the resolution of images. So if we have a low quality image, can we use super resolution to improve, to increase resolution, etc. It's quite widely used in Photoshop and a variety of that. One can also consider some of the data sets that we deal with from numerical models, etc. So if we consider the outputs of the forecast of precipitation for a region, one can consider them an image and indeed a low quality image. So can we take aspects from super resolution to improve the resolution of that image from a weather model or something of that nature? So there's been a number of approaches related to, there's been a number of investigations related to that. So this is the traditional super resolution based approaches here, where we take a high resolution image, we downsample it or compress it to a smaller size, and then we can quite easily reverse that with super resolution, etc., down back to a higher resolution again. Within a physics approach, the fundamental framework is quite similar. So if we have, for example, satellite data of land surface temperature or sea surface temperature or something of that nature, with that is of lower quality with data gaps, etc., can we increase the resolution using super resolution? And the results were that we had some success with super resolution, but there was some volumes of noise as well. What instead we looked at was, contrary to images, outputs from observation of environmental systems have specific continuity and consistencies in space and time. We know what those consistencies should be based on advection diffusion. So if we have temperature in with a given temperature in at a point in space, we know how, or we can resolve or predict how that temperature will transport in space based on both the advection and the diffusion of those variables or that temperature component. So can we use this information to inform the super resolution model? So rather than doing a purely data-driven approach, can we take what we know about the advection and diffusion of a space to guide that that mapping towards the super resolution image or the high resolution representation of the data? And in effect, what we're trying to do here is quite similar to the previous example. How can we inform or constrain the optimization component, cognizant of what we know about the transport from a physics perspective? So we create we have a advection diffusion model here. So here we have the transport, and the transport is function of time, the transport is function of space, and the diffusion component, with this being a source component here. We can represent this in terms of the physics loss function, in terms of the representation of the super resolution loss, together with the representation of the ground truth image, or the training data, so to speak. And we can combine this with our loss function for the approach, where we have our loss function pixel to pixel here is our classical loss function, where we are aiming to condition our prediction based on the observation, and our modified or introduced loss function here constrained based on the outputs of our advection diffusion model. And what we show after by introducing these and by taking the different or the outputs of the advection diffusion model in terms of the different representations, in terms of the temporal component, in terms of the spatial component, and the diffusion component, and combining with the source term, the source or sink term S here at the bottom, we can get a representation of the image or the representation of the data that is more authentic or more representative of the actual true state as represented by our physics, by our training data, or by our labeled data. So what I want to move on, I'm cognizant of time here. So what I want to move on a bit quick here to is some work that we are doing around reduced order models. And what we are aiming to do here is, can we accelerate certain components of the machine learning, of the high fidelity simulation models, by substituting with machine learning based models? So the idea here is, we have some sparse data, we have a simulation model or a high fidelity model that we can combine with data to generate training data for our to generate our reduced order model. And this provides us with certain advantages in terms of we can generate an almost infinite amount of data from the simulation model. We can replace complex, computationally expensive solvers with kind of fast, cheap, reduced order machine learning models. And we can do all this in an online system. So as new data is becoming available, we can infer and deploy, etc. again, and update model training, and have some optimal selection of when to run the expensive high fidelity model versus when to run the simple low cost deep learning surrogate model. There are disadvantages then, primarily in terms of our simulation model. We have a very strong theoretical knowledge of what it represents, what it contains, etc. We do not have the same for the machine learning side of things, since it's in effect a representation of data rather than a direct representation of our knowledge, etc. So we did this for ocean wave data in Monterey Bay, and what we observe is it performs very, very well. The machine learning model can readily learn the characteristics of the high fidelity complex simulation model, and it allows us to deploy and allow for very significant computational speed up, etc. That also then raised a few questions for us in terms of what else can we do. So one of the big challenges that we faced with the reduced order model is, yeah, we can do it for Monterey Bay, etc., wherever. But if we want to move somewhere else, then we have to redo this. We have to redeploy. We have to deploy our simulation model again in the new area. We have to train our machine learning model on the outputs of that simulation model, etc. So there's significant complexity involved there. What we are interested in instead is, can we do this in a completely independent manner? Can we deploy, can we take the outputs of a simulation model, use that to generate a reduced order model, and in effect piece together different machine learning models to allow for a more complete representation of a system based on the data that's available, so to speak. So without having any requirements on the data being structured in a particular way, without any requirements on the data being uniform in space, uniform in time, etc. And without any strict requirements from a particular boundary perspective, or whether data and the simulation models need to represent and account for specific data sets or specific behaviors at the boundary, etc. So what we were looking at then was a way to take these individually or independently trained models and concatenate them or combine them in some consistent manner that would approximate continuity. So again, coming back to what we can say about the theory of deep learning, etc. There are limitations about what we can say from a complete theoretical representation. But can we say that it approximates a continuity across the different domains or across the different models or approaches that we represent? So this slide is something that I'm not going to dwell on, but what in effect we looked at was treating each individual subdomain or each individual model as a discrete subdomain, where the machine learning model learns the characteristics of that high fidelity model within that domain or subdomain. And then we implement a recurrent neural network type framework between those individual models that concatenates them together into a uniform entire grid. So if we consider it from this perspective, can we learn a machine learning surrogate model on each of these individual pieces and piece them together in a consistent manner? And by introducing a Lagrangian relaxation at the boundary or interface between these different subdomains, it allows us to combine these in a consistent manner. And further, it allows us and opens up the possibility to bring in much more sophisticated relaxation coefficients. So rather than a relatively simple Lagrangian relaxation as we do here, we can bring in additional knowledge that we may have from outside the domain and impart to the training and learning of the machine learning model. So it provides a significant opportunity there to apply to different scenarios, etc., different configurations, etc. And the final thing that I wanted to talk about is the combination of the hybrid physics and machine learning perspectives. So this is looking at that. How can we, if we consider the high fidelity simulation model approach with a data-driven machine learning model approach, a kind of low order reduced cost, then how do we optimally combine these different systems? And one approach here is various ensemble aggregation approaches that allows us to have a small number of high fidelity or complex models, high fidelity, expensive simulations with multiple or many low cost machine learning simulated deployments. We can weight these in an intelligent manner. So we can weight on a combination of how well different models perform and also possibly on what we know about individual models or what we know about the past performance of individual models from a heuristic or a other approach, or from purely a which models performed well in the past. So by combining a machine learning based approach that learns the weights to assign to those models together with a blend of a high fidelity physics based model plus a machine learning based models, a large number of machine learning based models, it allows for a combination of physics plus machine learning approaches in a more robust manner, where we can, during extreme events or outlier conditions, for example, we might lean a bit heavier towards the physics based models that contains this information on that this situation might be an extreme event, etc. In more normal times, we might be relatively happy with the pure machine learning based models, the low cost, cheap to deploy, easy to set up models, etc. So it provides a system a framework to optimally combine these in a variety of ways. And this I'm not going to dwell on, but it's an area that is quite interesting for this combination of problem is the idea of optimal transport and some of the work that is done there. And optimal transport at its simplest level considers the work that is required to move a distribution or a body of work from one area to another. In environmental application in particular, it often makes sense to consider data in terms of its distribution rather than in terms of a scale or representation due to the importance of continuity, etc., and due to the complexity in space. So we're exploring quite a bit now the potential to condition the gradients or the difference or the optimization or learning of loss functions based on the distribution as opposed to just the pixel to pixel comparison. And this simply summarizes what I've been talking about a bit. There's a lot of work to be done to bring machine learning to fruition fully on science and engineering. It has not had the same degree of impact due to data challenges, but due also to the risks of overfitting and due to the challenges of representing extreme conditions, due to challenges of trustworthiness and reliability, etc. By explicitly informing and incorporating the physics-based approach, we can learn on smaller data. We can provide more robustness by constraining by what we know, so we can explicitly constrain to avoid unrealistic conditions or unrealistic representations. And we can communicate better if we know the physics of a system and if we know that those physics are represented within the model. We can confidently describe what the model is doing and how it will conceptually perform in different deployments and different applications and scenarios, etc. And I think two things worth highlighting here is there's a large number of options, techniques, etc., that you can use from a physics-informed machine learning perspective, and there's a lot of exciting tools out there. So there's been huge advances done in the past year or two, I believe, in this space. And what it takes, I think, or what it's looking for is how do we apply those tools to actual real world problems to generate impact and show the value of these, machine learning to these different industries, to engineering, to environmental science, etc. And I think that's all I had to say.
That was fantastic. Thank you. And if anybody has any questions, I have one I'm going to read out in a second, but if you have some, throw them in the Q&A or even in the chat. They're wondering, is there a minimum threshold for the number of observations for a determined area grid for meteorological prediction models to base its prediction on?
It's a very interesting question, actually, because the talk from Andrew Ng was, he raised this question as well and did a poll. And the volume of data that people work with in machine learning, it varies from a couple of thousand to 10 or 100 billion. So it's it very much varies based on the complexity of the data, etc. So if you're learning a linear system, you need 2 points, I guess, is the starting point. But really, environmental systems are complex, and especially if we want to represent outlier events and aspects of that nature. So it is something that is not to be underestimated. But what I would advise there is start with the data, and it's easier to start with data and go from there rather than try to have all your data in place before you begin.
It's a great one, and I think it's one of those answers too where it depends is kind of the answer sometimes for a lot of these questions, isn't it? Unfortunately.
Yeah, and I would that's what I would emphasize as well, is take an iterative approach with it. begin, see how it performs, get more data, see how it performs.
Right. And yes, I think your example of things you run into depending on your data, like cloud coverage for satellite data, right? Like there's the satellite's only going around so many times and you only get so many instances, and there's going to be all these challenges with it. This has been great. Question. You could say that one of the weakest, I haven't read it before, so I'm gonna have to read it out loud. I hope there's no swear words. You could say that one of the weakest components of climate models is a set of various parameterizations we use to either represent what we don't know, to model certain aspects due to computational constraints. Do you foresee machine learning replacing that aspect of climate models?
Yeah, so that's an excellent question. And what have been worked on now in terms of developing a complete digital twin of the Earth in the next decade, and the strides that are required there. Many of these extremely complex and computationally demanding aspects, these have to be accelerated in some manner. And how that will be, the truth is that we currently don't know, but it does require significant advances, significant experimentation to arrive at that final representation. And and I think that's where so if we take in the digital twin, what it will end up being is some combination of physics models and these really expensive climatological models with some reduced order models, and some components of that being accelerated with machine learning, etc. And it's a very active area at the moment. But if you look at what's operational still, it's still very much the old school WRF models or whatnot, with the very old school PD-based approaches.
Yeah, I think it's an evolution in time. And I think you referenced this before, it's all disciplines are learning how this can be applied. So whether you're a small business learning how to apply this, whether you're a physical oceanographer, you're still trying to figure out how this all works and how you can take advantage. I don't see any other questions. And I want to thank you so much for that incredible talk. I learned a lot. This will be posted online. If anyone has any questions, maybe they can seek you out on the World Wide Web and find some interesting way to connect. But thank you so much for sharing with us. And anyone who's interested, this will be posted online on our YouTube page. And if you ever want to reach out, you have other topics that you would like to explore, we'd be more than happy to cover those off. So thank you very much, Fergal. It was great to see you.
It's been great. Thanks so much for hosting. Really appreciate it.
Thank you. Bye, everyone.